Hello everyone, welcome to the section 2.5 notes where we are going to keep talking about functions and graphs, and specifically we're talking about transformations of functions, where transformations, there are many types of transformations, but it means changing the graph. We can change the shape of a graph by, can you think of some transformations? What comes to mind first? There's an overarching type of transformation which is called translation, and we will break this up into two different types of translation, where translation is like a sliding, where you don't change the overall shape, you just move the graph around. So we can move up and down, we can move left and right, and these are types of translations which in turn are transformations. We can also do some various types of reflections, reflecting across different axes. We're going to look specifically at reflecting across x-axis, reflecting across the y-axis. We could reflect across other axes, and there are stretches that we can do. I will say stretch/compress. We can also do these in the horizontal and vertical directions. And in general, you might call this also dilations for stretching. And then compressing, it could also be called shrinking if you like. But there is another type of transformation that we're not going to cover. It's outside of the scope of this class, but there is a way to transform graphs which is by rotation. And it is a little bit more complicated to achieve this one. But these first three types, first three basic types, even though we'll have the different versions left and right direction versus up and down, or you can think of it as being in the x direction versus the y direction, we'll be able to achieve all of these by manipulating the equations for the functions. And it doesn't matter what the function is, if we do the same manipulation, we can predict which type of transformation is going to be 100%. And so first, just thinking back to symmetries, the way symmetries work, wondering true or false, the graphs of y equals x and y equals x cubed, these have the same type of symmetry. First, we'd have to know which type of symmetry they have. And a big part of this section is being familiar with the overall, that's not a very straight line, the overall types of functions that I would call parent functions. Parent functions refers to the basic type of function that we would take and change the equation slightly in order to achieve some transformations. And so we have this very basic, it is the parent for all linear functions, which is y equals x. This one is a cubic function, y equals x cubed. You should also know what some of them look like. Y equals x squared, which is a parabola like this. There's absolute value of x. Here I'm going to label this one y equals x squared. Absolute value of x, which is this v shape. You should have an idea what these graphs look like. And there are some more that maybe we'll see, maybe we'll list as we go down these problems. But just looking at y equals x and y equals x cubed, can you tell which type of symmetry they have? For sure they're not symmetric across the y or the x-axis, but they actually are both symmetric across the origin, which is that they have the points that are opposite the origin from each other in common. Say this point out here, we just go straight through the origin, that same point is right out here. And we have it on the line as well. So they do, yes, I will say yes, they do have the same type of symmetry. And some transformations actually will preserve the symmetries of graphs. That is something of interest. But number 2 right here, looking at what's probably the easiest type of transformation to accomplish with the, and maybe to remember also what it does, is a translation. The translations are very easy. This one is translating in the vertical direction. Well, we can see if we take the graph y equals x squared, if you just subtract 2, this part of the function already, the x squared part, this is the normal function. So we're taking that regular function which is describing a y value, you plug an x in here, you square it, you get the y value. So this, which we can say this was f of x, is there, the x squared. we're taking that original f of x function, and then outside of there, we're subtracting 2. The minus 2 is on the outside of f of x. So we end up with something that looks like this. G of x, it was our original function f of x, and we subtract 2 from it. These are y values. And so we're subtracting 2 from all the y values, which achieves a translation down by 2. So instead of our function being here, y equals x squared, which you should know, we will have this one shifted down by 2, y equals x squared here. And then we have the horizontal type of translations. These are also pretty straightforward. But notice here, the function itself, absolute value of x, that's sitting there, that's the f of x. Here there's something going on inside of the f of x function. It's not a plus 4 on the outside. If we had absolute value of x plus 4, this would be a shift up by 4, up 4. This one, the shift is happening inside of f of x. We're changing the x values. It's happening to the x values. We're increasing the x values by 4. Now, all of the things happen in the x direction. To me, it seems a little counterintuitive, or it's like it does the opposite of what you would think. So when we add 4 here, this does not go to the right by 4. If you look at a table of values, you could confirm this. But when we have something of the form, we're putting inside of the function, adding something like this, then this does a shift to the left. Shift left by whatever amount we are adding to x. So in this case, I made it shift left by k. But here, we're shifting the absolute value graph to the left by 4. So instead of being here, this absolute value graph, we should have over to the 1, 2, 3, 4, we should have this absolute value graph, this one. And now, looking ahead, we will get into the reflections, which is that if we take the actual function itself, which remember anytime you have the f of x, here y cubed is in the place of f of x, this one is representing the y value. So if we put a negative sign out in the front of this, like here goes x cubed, is there, we're putting the negative out in the front. So it's like negative f of x. We're taking all the y values and making them negative. And so this becomes a reflection across the x-axis. And for this, we have x cubed. So our normal x cubed function goes like this. We're taking each one of these y values, like here's a y value, we're making it negative, so it should become down here. Or these y values that are already negative, say this is -1, we should times that by negative and make it go +1. And so we end up with this graph, which is reflected across the x-axis, like this one. And now looking at another type of reflection, here we'll see it just on this graph. I'm going to switch back to blue, and we're wanting to do something else. Now notice instead of the negative being in front of f of x, the x values are being made negative. And when you take an x value, like here the x value is +2, with a y value also of 2, we should make the x value be negative. So it should become this point -2, +2. And this is, as you can tell, this is making a reflection across the y-axis. And if we do that for all of the points, we take this one, should also come over here. Take this point, it should land over here, become the -1, and vice versa. This point comes over here. Then we will have this graph. I should have done those in red. The point 0, 0, if you make the x value negative, it will not change at all. But we end up with this alternative zigzag, which is reflected across the y-axis. And then besides the reflections, we've seen the two reflections, x and y-axis reflections. We can do the stretching and shrinking. Why don't we take a look at these? Which here, again, always thinking, is the transformation I'm always just wondering, is the operation happening to the x or y values? Is the transformation affecting the x values or the y values? That can help you determine, is it in the up and down direction or the left and right direction? And so here again, we can identify our function as x cubed. So if we look in the transformed version, there's x cubed. We can isolate it. X cubed is the y value from the original function. So when we multiply by 1/2 in the front, we are multiplying the y values 1/2 times the y values, which means it's a vertical shrink. And for this one, x cubed, we've seen it already. I'm just going to give a rough sketch for how it should look if it's shrunk by 1/2. There's x cubed. We shrink it by 1/2, so all of these y values, this one, it should be half as much, say there. This one should be half as much, let's say there. And same for all of these, they would be half. And so I'm just looking, what would be the halfway point in between there? And we end up with this function. If this were on an actual grid, it would be easier to see the half values. But the next one, you can maybe predict what we're going to be dealing with. Even though here again, it's something that's happening in the x direction, you have to be careful because it can do the opposite of what it seems. Really, what you have to think of is the x values, they go into the function. So, if you're making a table of values, like here go the x and y values. If we are plugging something into here, say we plug in 1 for x, it actually gives us the y value that corresponds to plugging in 2 for x. And so if we plug in 1 into the transformed version, it should give us the same y value that we would get by plugging in 2 over here because it goes 2 times 1. And so we would end up with this point, 1, 2, because f of 2 times 1, right here I'm plugging in x equals 1, into g, see g of 1, we take f of 2 times 1, which is f of 2, which is 2. So g of 1 is 2, so we should end up with this point over here, 1, 2. But see, this actually moved this x value in towards the y-axis. It did a horizontal shrink. So this right here is performing horizontal shrink whenever we have f of something times x, or this something is greater than 1. In this case, for this problem, it's 2. So it actually shrinks everything by 1/2, which means this point out here, 4, 0 should land on 2, 0. We just divide all the x values by 2, so it comes here, negative 2, 0. Negative 2, negative 2 should land on negative 1, negative 2. And we end up with this scrunched up version. Oh, sorry, that looks... Now all of this red is very bright, but I will switch back to blue for the next one because we're going to, on the same graph, try to achieve this transformation, which is a horizontal stretch by 2. And so here what we should do, even though some of these are going to fly off the page, just go 5, 6, 7, 8. This point comes out here. That point comes there. Multiply the x value by 2. Even though here it says half x, you just have to get it straight for these, that the x transformations, it does somewhat the opposite, and it might help here to plug in, if it does help for you, just a table of values. We're going into g with these values. So here's y equals g of x. And if you plug something into g right there, like say we plug in x equals 2, we're finding g of 2, which is going to be f of 1/2 of 2, which is f of 1. And so it would take this f of 1, which is 1, and that becomes g of 2. So the point lands there. And that's on the way towards having this point. So we have this elongated, horizontally stretched zigzag like this one. This point's coming out to negative 4, negative 2, and then negative 6, negative 7, negative 8. We have this graph, is the blue one, which is g equals f of 1/2 of x. And now there's a big consideration to be made when there are multiple transformations happening at once. Because the order of transformations, it is important. And if you do the transformations in alternative orders, then sometimes you can get a different effect. So this order should be followed carefully, order of transformations, even though they're not, it's pretty easy to figure out. We don't have to remember every single transformation in order. It's that they come more like in groups. The first transformation that we should do, though, is that we basically do all of the horizontal stuff first. And that's a way of splitting this up into just two ideas, that you do the horizontal stuff first, and then you do the vertical stuff last. But the very first horizontal thing that you should do, and it does actually line up pretty closely to the order of operations that you would have for PEMDAS, doing parentheses first, then exponents and multiplication and division, and then addition and subtraction last. You notice whenever you're doing a horizontal shift, that's happening always inside of some parentheses like this. You're doing x either plus something or x minus something. This one in particular is going to the right by 3. Remember, subtracting 3 from x actually goes to the right by 3. And that should happen first. We do always the horizontal shifts first. And then we still want to do something horizontally. What else could happen horizontally are the reflections. Reflect across the y-axis, and any kind of horizontal shrinks. This can happen right now. It would shrink, or stretch. That happens next. And now we're done doing everything that can happen horizontally. We should mirror this by doing these same ones but in the opposite order. So now we should do all the reflections in the vertical direction, which means reflections across the x-axis, and vertical stretches and shrinking. That happens next. And the very last thing, we want the vertical version of the shifting. So we will do vertical shifts. Will be the very last thing to do for the transformations. Now let's see for this one specifically. We do only have 3 types of transformations. We've got shifting to the right by 3. We should do that one first because that's a horizontal shift. So this one, I will come over here now. Say this is the first thing to do. We have also, this will be this third category of transformations, which are it's not a reflection though, it's the vertical shrinking. This multiplying times 1/2, this does vertical shrink. And then the very last thing will be this down by 2, the shift down by 2. And so we will do them in this order. Right by 3, we do it first, and then do the vertical shrink. Lastly, we will shift down by 2, and we're doing it to the graph y equals x squared, which means we're going to have a parabola, y equals x squared. I'll just draw the original one. And then what we should do, I'll draw these as dotted lines. We should go to the right by 3. So 1, 2, 3. We end up with this one. And I'm not being too careful about where they intersect each other or anything like that. Just getting a rough sketch. Next we want to shrink it by 1/2. So I want to take all of these points. And now I'll do it a dotted red line. This is happening next. We want to shrink it vertically by 1/2, like this. And then the very last thing, I will make it the solid red. We want to go down by 2. And so it will land here. It's been stretched like this. Really, I mean to say vertically shrunken, but it turns out there would be a transformation that you can do which would be a horizontal stretch, and it would look identical to this. So you'll never be tested on just looking at a graph whether it was a vertical shrink or a horizontal stretch. It's impossible to tell by looking at it, but you can tell even in this one. Making a horizontal stretch stretches it out left and right, like this one. But that's the same thing as compressing it down vertically. So horizontal stretch, I'll just write that one. Somehow it's the same thing to a vertical shrink and vice versa. Vertical stretch looks like horizontal shrink as well. And so that does it. If you keep these order of transformations in mind, you will get it correct every time. I know that in the examples on the left side, it was focusing very much on moving individual points. I don't think of it as much as moving individual points, because for me, filling out tables of values, it's kind of tedious. I would rather be able to just graph the overall shape. Even though when the graph is with points like this, individual points, and it's a weird graph, it's this piecewise type of thing. In that case, it is easy enough to move the points, but we're not creating the table ourselves. We're just looking at the point, moving it. But I hope this was helpful to you, and I'll catch you in the next video.